All right, let's get started. All right, now that you are drunk because of all the information I gave you, let's try to make a little bit of order, and we're going step by step across all the processes that I highlighted. So first topic that we're going to discuss are quantum gases. And as I mentioned, we are going to consider quantum gases because we are at the very early times of the universe, and we are dealing with ultra-relativistic particles as well as non-relativistic particles. But we need to know and understand to deal with all of them. So how do we do that? So we are talking about gases, and this means that we are dealing with an extremely large number of particles. Therefore, we are not looking at the story of each individual particle and try to find the equation of motion of one or the other, but instead, we are going to have a statistical description of our fluid. Statistical description that is going to give us ensemble properties, so properties of portions of the gas containing a large number of particles. Therefore, we are going to define volumes of this sort. There are the particles that are doing whatever they are doing inside that volume, and for this volume, we want to know, for example, the pressure, we want to know the entropy, we want to know the density, we want to know the number of particles that are inside those little volume, right? A characterization of our fluid. How do we do it? Well, particles are, we start by the characterization of the particles. What do they have? How do you characterize one particle? Position at a certain time, right? What is more interesting than time? Well, we can have an evolving time, but we have also the velocity, meaning the momentum of the particles, and we call it p. And of course, this might be a function of time. All right? Therefore, we know that a particle is here, and it has a certain momentum, so it's moving in a certain direction with a certain velocity. I'm using the momentum, not the velocity. Why? What about photons? Right? What about massless particles? Velocities start to be difficult. That's why we're going to use the momentum, because it's common to all particles. This is a 6-dimensional space, because we have 3 dimensions plus 3 dimensions, and all the combinations. So you have a 6-dimensional space that looks like that. Let's take, for example, the x1 and momentum 2. I don't know. That's a slice into 6-dimensional space. And we might have a particle somewhere here with a certain position and a certain momentum. Is this correct? This representation. We're talking about relativistic objects, and we are talking about quantum objects. No, this is wrong. Exactly, this is wrong. Why? Because, or we know, the better we know the momentum, the worse we know the positions. The better we know the position, the worse we know the momentum. We have the Heisenberg uncertainty principle, right? Therefore, what we do, what we consider is not, the phase space is actually a continuous variation of parameters, but instead what we're going to do is to pixelize it, if you wish. We are going to create boxes, and each box, let's take this one because the particle was here, let's take this box here. It has a certain width in position, the x. It has a certain width in momentum, the p. And the determination principle tells us that dp dx is larger than h. So we have discretized our phase space. That's how it is called. Phase space. That's the space. That's how this space is called. And it's discretized accounting for the Heisenberg indetermination principle. And a particle here is exactly equivalent to a particle here. No distinction. And therefore, this one represents a state, and we can call it alpha. Okay? This is another alpha state, state 1, state 2, state 3. Okay? So same position, we might have different momentums. And momentum is associated to energy. So we have different energy levels for the particles that we are considering. Yeah?
I've got a question about the quantization. So you're drawing the position along the one direction and the momentum along the two directions. So in principle, the position and the momentum operator should compute in x1 and p2. So we cannot, like, the uncertainty principle is not in unequal dimensions. Right? So, like, this whole quantization business only works if you consider the same spatial dimension as the same momentum dimension. So x1 and p1 then draw on a grid, but not in x1 and p2. Right? Because
Yes. Yeah. But I mean, yes, you're right. P1. Yes, no, it works. Yes, exactly. Yeah. Yes, it's in slices. Yes. Okay. Now we made order. Thanks. Good. And here we are. Right. Therefore, the game now, as we said, is a statistical description of our quantum gas in which the particles are going to fall in different locations. And as I said, we don't care to track the trajectory of each particle to see how the overall system is behaving, but we are interested in knowing what is the probability of having a certain number of particles in a certain cell of our phase space. Okay? Therefore, we have our probability distribution. So F is going to tell us what is the probability of having a particle in the state alpha. And of course, our F alpha is a function of position, momentum, because it characterizes the cells, and if the system is dynamical, of time as well. All right. Then there are different kinds of ensembles that we can consider. And with ensemble, I mean a collection of a large number of particles that can also be or not in connection to other, a thermal reservoir, for example. And this created the distinction between different ensembles that can be microcanonical, in which we have U, that's the internal energy of our gas, because our gas has also an internal energy. If you take one portion of your fluid, it can have a certain amount of energy content. We keep this, the number of particles and the volume fixed. Okay, so that's a closed system. N is not changing, the energy is not changing, the volume is not changing. Then we have a canonical ensembles. which is more interesting, because in this case, what we are going to have is that the energy is not fixed. And what is instead fixed is the number of particles, the temperature, and the volume. This is fixed. Okay? So you can consider an isolated system which has its own temperature, fixed, that can exchange heat, because the temperature can change, with a reservoir. Okay? And the two, if the heat exchange is efficient, the two temperatures are going to be the same. Okay, that's the thermal bath that acts as a reservoir. Then for this sort of canonical ensemble, we know what is this guy from statistical physics. And that's the Boltzmann distribution. So we have our F alpha, which has the Boltzmann factor, epsilon alpha over kT. So we have the energy of the associated to the alpha state divided kT, where k is the Boltzmann constant. And this must be a probability, so it must range between 0 and 1, and we have a normalization factor that we call canonical partition. That's our ZC. And ZC, since this is the normalization of this quantity, is just the sum of all with respect to all alphas. Canonical, that's the canonical. Partition. Then a quantity that is extremely useful and relevant is the Helmholtz free energy. Which is basically coming from our canonical distribution, because if we define F alpha as e to the minus epsilon alpha over kT, divided the partition sum, we can plug in our definition of the partition sum, and we end up with e to the f, this is our definition, over kT, times e to the minus epsilon, minus epsilon alpha over kT. So we are defining this guy, this f, related to the inverse of ZC. And if you want, just to have epsilon alpha over kT. That's another way of writing the distribution of our f with respect to the Helmholtz free energy. Why is the Helmholtz free energy useful? Because F is telling us what is the difference between the internal energy of our system and the work that the system can do, Ts. And basically, the free energy is nothing but, you see, if you look at this expression, this is a Legendre transformation of U. So it's a way, if you want, to re-express the internal energy, and looking at what is the difference with respect to the work that the system can do. Then we can look at the total differential of the free energy, which again, remember, it's for a fixed temperature, volume, and n. And with this df, yes, we are keeping this y, these three parameters fixed, but the meaning of this is a function, and therefore we can always define the differential function. If the difference of this guy is going to tell us, basically this df is going to tell us what would be the difference of two systems if I change by a bit the temperature, the volume, and n. or one of those separately. Okay, all of them, some of them, all of them separately. So this is just the total differential. So we just get the total differential of this function. And therefore, we have the u minus t, the s, minus s, the t. Total differential of this function. Nothing but that. Then what we can do is to plug in our an explicit expression for the definition of U, of the internal energy. Therefore, we have T, the S, minus P, the V. Remember, first law of thermodynamics. That's part of the laws of thermodynamics. Plus mu, the N, where we now, the U contains the chemical potential. And you see by this expression, it tells us what is the difference the difference in the free energy that we get by adding or removing particles to the system, the N. Okay? That's what's the meaning of this guy. And you can already have the intuition that when we'll allow the system to change the number of particles, this is going to be extremely important for the reactions, right? Because reactions change the number of particles. All right. And then we have the other two terms. So T, the S, minus S, the T. And then we have minus T, the S, plus T, the S. They get cancelled away. If we continue, what is left is minus S, the T, minus P, the V, plus mu, the N. Fantastic. Now what I said earlier, it's even clearer, because the change in the free energy depends on the change of the temperature proportionally to the entropy of our system, a change in volume proportional to the pressure of our system, and a change in a number of particles given by the chemical potential. And now, as I mentioned, this is the total differential. Therefore, you see that S is nothing but the T of F per the T, right? Total differential is just the derivative of F with respect to T, with respect to the temperature, times the T. And the same for the other quantity. Therefore, we're going to have that's with respect to the volume of F in the volume, plus the with respect to the number of particles of F, the N. And this gives you a directly relationship between, this shows you that once you have the free energy, you get the derivative with respect to time, and you get, for a fixed temperature, volume, and number of particles, you get the entropy. You take the derivative with respect to the volume of the free energy, and what you get is the pressure. You take the derivative of the free energy with respect to the number of particles, and what you get is the chemical potential mu. Okay? Don't forget about the minuses, okay, that enters into the definition. So minus the derivative of Tf is the entropy. Minus the V of F is the pressure, plus the N of F is the chemical potential. So at equilibrium, so when the system is in thermal equilibrium, it reached the nirvana, then F is a constant and is the minimum. It has the minimum value that it can possibly have. Again, at equilibrium, we can look what happens at the chemical potential. So, of course, T is constant because we are talking about a canonical ensemble. Then as well, the volume is a constant, again, because we are talking about a canonical ensemble. And at equilibrium, mu is equal to 0. Why? Well, that's easy to prove. We just go back to our df, which is equal to minus s dt minus p dv plus mu dn. But if t is constant, what is the t? 0. If the volume is constant, what is the v? 0. What are we left with? With this guy here. Because the differential, this guy is not changing, that it's equal to 0, and this implies the fact that mu is equal to 0. Yeah? N is fixed. Yes, but this is the F fixing, what is it? Temperature and volume. Okay? This would be how the energy of, what is the change of the free energy, which is a function that has 3 variables, would differ if we have a change in the number of particles. Equilibrium tells you that mu is equal to 0, meaning that you have as much particle created and destroyed, right? The reaction goes in both directions. So just to be clear, so for example, here, when I said that, for example, the entropy is equal to minus the F over dt, that's once you fix the volume. Okay? For a fixed volume and n. And so on for the other quantities. Okay? Where you fix the other variables. All right. Then even more interesting, because here we have a system, I mean, we studied the properties and so on. We have a system with n fixed. Now we go for something which is funnier, which is the grand canonical ensemble. Which is a generalization of this one, and deals with open systems. In this case, n can change, meaning we have our reservoir, and our system is not a closed box, but is open. We have an exchange, also in terms of number of particles with the reservoir. All right, what is fixed here? N can change, so this is very important. That fixed, what we have fixed is the temperature, the volume, and the chemical potential. So you see, we exchanged the fixed number of particles for a fixed chemical potential. Now, what is the number of particles that we expect? Well, this is going to be the sum of the number of particles in each state. That's trivial. What is the energy of our system? Again, for the state alpha. Is going to be the sum of alpha. One particle contributes with what? With, one state. So n particles in that state, with how much energy contributes. Each particle contribute with an epsilon alpha energy. That's the energy of this level. So that's the energy of our system. What is now the partition, the distribution for our particle of the state of the states in our the phase space distribution of our particles. Well, that's going to be similar to what we had before. So we have the energy of the particle of the state alpha minus mu n alpha over kT. And of course, we have a normalization, which is not the one that we had earlier, because now the sum is running over all of that. Grand canonical. Now we cut short the derivation of the grand canonical ensemble. So just to give you the definition now. So it's just the sum of E alpha minus mu n alpha over kBt. So I use k always, let's stick to k, as we did before. So there's no conceptual difference. But then look what happens. We have the exponential of minus E alpha, and here we have minus this one. So I can transform it into the product between exponential. Minus becomes a plus, mu and alpha. Okay? And we can transform, therefore, the summatory in a productory, in a product. Because this is, yes, exactly. We want to do the steps. No, let's cut it short. So you can rewrite it. You find it in the lecture notes. I don't want to go too much into details in derivations here because this is just a recap. So that's going to be the productory with respect to the summary of all the energy level per state, mu and alpha over kT. But the key concept lies here, okay? We can change this one in that, and we are transforming with a pi. So now to be more precise, this will be with respect to the n alpha, to the number of ensemble of n alpha state. Okay? So we can call this guy Z alpha. So that's the partition sum of the alpha state. Now what can we do? Well, in analogy of what we did earlier, we can create another free energy, which is not the one of Helmholtz, because the partition sum is different. But we are going to define what is called the grand canonical potential, and we call it phi. How is it defined? Phi, given a temperature, volume, and a chemical potential. So you see the key variables are the one of the fixed, of the system, that are characterizing the system, and that's equal to minus kT ln of z gc. Okay, full analogy of what we did earlier. Then we can, again, apply a Legendre transform, because this one is related to the Helmholtz free energy. Okay, remember this is a generalization. So TV mu is equal to what? The Helmholtz free energy, which is TVN minus mu n. Okay, so F minus mu n. It's a Legendre transform, like there. F was the Legendre transform of U. You see F equal to minus the product of two things. Here we have F minus the product of two things, where this is fixed and n is the number. Okay. Then we can plug in our definition of F. We put it here, and what we get in the end is U minus Ts minus mu n. Again, phi Legendre transform of F. Then we can go for the differential as we did earlier. Therefore, the phi is going to be equal to the f that we already know, we already computed, minus n the mu minus mu the n. Okay? So this is the differential of the f, and then we have the differential of these two guys here. Well, I can plug in my free energy here that I take from up there. There are terms that are going to cancel, and in the end, we are left with S dt minus P dV, which are coming from the free energy. And then we are left, this other term is going to cancel, and we are going to be left with N the mu. Again, this is our total differential. So you see that this guy must be equal to the phi with respect to the temperature, the T, plus the V of our potential times the volume, plus the mu of phi times the mu. And again, you see we have a relationship between entropy, the derivative with respect to the temperature of the free energy, pressure, and the derivative of the free energy with respect to the volume, and the number of particles with respect to derivative of phi, of derivative of phi with respect to the chemical potential. Again, just to be super explicit, I just do it for the entropy as I did earlier. We have the minus, which is coming from here. And then we have the F, the phi, let me write it explicit. So that's the dt from there, which is computed for a fixed volume and a fixed mu, so the other variables. And the same goes for P, and the same goes for N. Let's give a look now at the chemical potential, which is one of the key actors for what we are considering, right? What is it expressing? Look, it enters here, and it tells us what is the change in the free energy once we introduce a new particle. We change the number of particles, and mu tells us proportionally how much the free energy is changing. Therefore, it quantifies the energy gain or loss of the system, therefore by adding of system, more precise, characterized by F, changed by adding, removing one particle. Therefore, what is the total change in our free energy? Well, it's easy. We have the summatory of our particles, and each, because they are particles that can be of different species, okay? Therefore, we might have the particle of type E with a certain chemical potential. And the total change is given by the sum of all of them. Okay? And that's important because we are considering chemical reactions, right? And we have to be general, and we can have species of different types interacting one with each other. For example, a scattering process, photon, electron, two different particles, same fluid, same pot of particles that we are considering. All right, then we have a total, we can define as well a total chemical potential, which is nothing but the sum of all the mu's. total mu. Why is it important, this guy? Because it controls the chemical reactions. Let's call, for example, J the type of particle. Might be a photon, might be an electron, might be a neutron, might be a proton, might be a neutrino, whatever you want. And in the system, we have a total number of particles, which is the sum of the number of particles for the different species that are involved. So that's the N, is the total number of particles. They can be different one from each other. And each of them can have a specific chemical potential, mu E. We use J, so that's mu J. Now we have an equation that links a reaction in which we have mu E plus mu2, so that's the sum of the chemical potential of two reagents. So these are two particles that are reacting one with each other, and at equilibrium, this must be equal to the chemical potential of the products of the particles. This is at equilibrium. And at equilibrium, mu is equal to 0. Okay, two chemical potentials, the energy change on the system given by adding a particle or removing a particle is the same on the two sides. So they are equal, okay? I can add a particle, but for the other one, it requires the same energy to go back. Okay, so the energy exchange, the effort that the system has to take is the same because the energy that you need to change one by adding or removing a particle is the same by both sides. Okay? In terms of reactions, we would have particle 1 plus particle 2, equilibrium, particle 2 plus particle 3. If we have this equality, here we are, the reaction in this direction is favored. Favored. Okay? Because here the chemical potential is higher, therefore to change the number of particles this side requires less effort. Okay? And it's going this direction. It's easier to add a particle. If it is going to be the way around, then the reaction is going in the reversed side. Okay, let's go it backwards. And I need to think about the chemical potential. Just last comment. Let's take an example, okay, to make it a little bit more, more real as a concept. Let's take a reaction that involves an electron and a photon. And we are taking, for example, equilibrium. And this can happen because the number of photons is not conserved. You can have an atom emitting radiation, right? So you have one particle, which is the atom, and it's throwing out photons. And outside, the number of photons is not the same. As well, an atom can absorb photons, so the number of photons is not conserved. If we now exploit our reaction for equilibrium, what we find out is that we have mu electron plus mu photon equal to what we have on the other side, where we have, again, an electron plus 2 photons, 2 mu of the photons. Here I have a factor of 2 because here are 2 different particles, but of the same time, of the same type. And they have the same chemical potential. Okay? These are these 2 photons. These are these 2 mu. Then what we can do? Well, we can just cancel terms. So this one goes away with this one. And we end up with the relationship that mu must be equal to 2 mu for the photons. What does it mean? When is this expression valid? When mu gamma is equal to 0. Then you have 0 equal to 0. It's fine. 1 equal to 2, no. Therefore, the solution of this equation is mu equal to 0. So in equilibrium, the mu for photons is equal to 0. Another example, very simple reaction. Let's take a whatever particle and the antiparticle. So it's an annihilation process. And at equilibrium, it's going to emit 2 photons. This is, if we now go for the mu x plus mu x bar, at equilibrium must be equal to the mu of the photon plus mu of the photon. But what's that? 0. What does it mean? It means that for particle and antiparticles, mu particle is equal to minus mu antiparticle. So you see that equilibrium, the relationship between different sides of the equation for the mu's, for the chemical potentials, are not free. Because why? We have a constraint. That's a constraint, right? So it reduces the degrees of freedom. All right. Let's go through the last topic. And what I'm going to kill is the microcanonical ensemble. Let's go right here. All right. Let's now to see how many particles we can make in one, we can plug in one of these cells, right? Because we are not completely free. Because we know that when you're dealing with quantum systems, particles can obey or not Pauli's exclusion principle. Therefore, if we are talking about bosons, where they do not obey the Pauli exclusion principle, we can put how many particles we want in the same state. If you're talking about fermions, that's not the case. They are obeying Pauli exclusion principle, and we can put only one. Okay? If we have something that has spin up, spin down, we can put 2 of those at the same energy level, because they belong to a different cell. They belong to a different quantum state. Okay. Fermions and bosons. So let's look at the partition sum. So we have the fermions that have a half spin. So the spin can be, for example, 1/2, 3/2, and so on. And they do obey exclusion principle. Pauli exclusion principle. Therefore, in one cell, what is going to be an alpha? We can have 0 particle, because yes, the state could be empty. We could not have anything. Or 1. We only have one state, one particle in a specific state, in a specific cell. That's what we can have. If we do that, we get our partition sum, our Z alpha. That's the probability of having the alpha state occupied. That should be there. Yes, that's down there. And we have a symmetry, but the symmetry has only 2 terms. We have a 0 and we have a 1. So it's a very simple symmetry. For our Z alpha is going to be 1 plus e to the minus epsilon alpha minus mu over kt. Fermi-Dirac distribution. For bosons, we are talking about the spins that are integers. Therefore, we have 1, 2, and so on, or 0. And in this case, no Pauli. And we can plug in how many particles we want. So an alpha can be 0. Again, an empty state is allowed. 1, 2, 3, 4, whatever, infinite, as many as you want. And in this case, we have Z alpha, 1 minus epsilon of epsilon alpha minus mu over kt, all of it to the minus 1. That's the Bose-Einstein distribution. Where is the symmetry gone? The symmetry sort of disappeared because we have the geometric series. You know that we have symmetries, right? And taken up with a series that have an analytical expression. That's the geometric series. That's what we used. Geometric series. Sorry, forgot an equal. Which is the fact that we are summing between n equal to 0 to infinite. We have a converging series of e to the power minus nx. And this guy converges to n minus x to the n. I can do that. And that's equal to 1 minus e to the x to the minus 1. So that's what was used here. When we transform that symmetry, where is it? The symmetry into an analytic expression. That's because the symmetry, the series converges. Then we can ask ourselves what is the number of particles in our state. So that's the distribution, the real distribution of particles. So number in the phase space, number this distribution. State. And what we do, we just use one of the expressions that we used earlier. We have our partition sum. We can find our grand canonical ensemble that, look, we can use to define the grand canonical partition sum. And we have the expression n equal to the derivative with respect to mu of phi. We just do a derivative. for the average number of states in that state is given by the phi with respect to the mu equal minus. So let me point the finger here. So n, so minus n is equal to the mu phi. We have phi, we just compute the derivative, and we have the number of particles in our alpha state. So we just do that. So we have minus and minus give us a plus, kt. And then we have the ln of z alpha over the mu. And then what we do, we just plug here our mu alpha for the bosons and for the fermions. I don't do the math because they are trivial, but in the end, you should already know the result. We find basically our distribution for fermions and bosons, which is the usual 1 over e to the alpha minus mu over kt plus minus 1. So you have plus or minus according to the fact that you have a fermion or a boson. So plus fermions minus bosons. All right. So here was a little recap that we are going to complete by considering an ideal gas, and that will leave us to explicit expressions for pressure, entropy, density, and so on and so forth for the fluids that we are going to consider. So everything started with the phase space distribution, so from the space, in which we consider particles in this 6-dimensional space, and where the exact location of the particle is sort of constrained by the uncertainty principle of Heisenberg. And therefore, we are sort of we are quantizing the phase space into cells, and each cell represents a state for the particles. All the particles that are following within this area belong to the same state. The game is not to look at the trajectory of each individual particles, but just estimating what is the probability of finding a certain amount of particle, I mean the probability of having a particle in a certain location. And of course, this transform, so more likely is the probability of finding a particle here. This gives us overall a larger number of particles in a given state. How do we find it? Well, first we need to characterize the system that we are considering. So we went through the microcanonical ensemble, in which we have the energy which is not fixed, but the system is closed. So we have a reservoir that is in thermal connection with our system, which has a fixed number of particles, so the number is given, temperature and volume, and the temperature is given by the reservoir. The distribution of the particles in the phase space is given by the Boltzmann distribution. That is a normalized function because it's a probability, so of course ranges from 0 to 1, and the normalization is nothing but the sum over all possible states of the function that gives the distribution. That's our canonical partition, out of which we can derive the Helmholtz, or define, better to say, the Helmholtz free energy by calling Zc the inverse of this exponential with the free energy is here. All right? Then we generalized a little bit, we relaxed the condition for what we are interested in, meaning an open system in which the number of particles is not anymore fixed. You see, n is open and can change, whereas what is going to characterize the change in the number of particles is given by the chemical potential. Then this has a different distribution sample, a different distribution in the phase space that contains an expression explicit for the chemical potential. Again, you can grand canonical ensemble, and exactly as in the same analogy as we did for the canonical ensemble, we can define energy, a free energy. In this case, it's not the Helmholtz free energy, but it's the grand canonical potential, phi, okay? Which is written like that, exactly as it's done for the other one. And then one can also realize the fact that this is actually nothing but the Legendre transform of the Helmholtz free energy. So we are changing the variables here. We have from n, we go to mu. Then there was a little bit of manipulations, and again, I showed you that the derivatives with respect to temperature, volume, and chemical potential of this grand canonical potential gives you the entropy, the pressure, and the number of particles. So that's key point, because we have, through this guy, the full characterization of our fluid. Then I gave you a few more details about the meaning of the chemical potential, because this is the guy that is ruling the reactions that we are interested in. And is the meaning of it, you see, we have the change of the energy is given by the change of the particles given what is the energy that is required to the system to change the number of particles. For the total change in free is nothing but the sum of the number of particles that you have times the chemical potential. The chemical potential depends on the type of particle that you are considering. Then I showed you how this chemical potential is controlling the reactions. Because at equilibrium, we must have that the sum of the chemical potentials of the particles that are reacting must be equal to those of the products. Meaning the total chemical potential, when you sum all of these together, must be equal to 1. Okay, so that's exactly the same expression. And if the energy, the total chemical potential of this side of the equation is larger with respect to this one, then the reaction is proceeding in this direction. To produce this one is difficult. To produce this one is easy. The reaction is going this direction. And of course, the way around. When this is easy to be produced, this is difficult to be produced, the reaction goes in this direction. Then I gave you a couple of examples. And this was about this grand canonical ensemble, which is the one that we are interested in. Then we started to dig into fermions and bosons, because yes, we now know how to derive the pressure, number of particles, and entropy and so on for a fluid, given a certain chemical potential. Given a certain partition, which we now need to specify, because we have this symmetry, right? And therefore, we need to specify the symmetry for the kind of particles that we have. And this depends on how many particles we can plug into a specific cell of our phase space distribution. And for fermions and bosons, the story is different, because for fermions, they obey the Pauli exclusion principle. Therefore, we can have only 0 or 1 particles in the same state. So, or there is a particle or none. And the symmetry is trivial, and we adjust that. For the bosons, they do not obey to the Pauli exclusion principle, and we can plug in as many particles we want. Therefore, we have a series which is infinite, which can contain infinite terms, but fortunately is a converging series to this guy, and we have this final expression. Once we have our Z alpha, we can go back to the relationship between the derivatives of the free potential to number of particles, pressure, and entropy, and derive explicitly those expressions. Here I gave you the example for the number of particles for the state alpha, and for bosons and fermions, you get this expression where the only difference is this plus minus, where plus goes for fermions and minus goes for bosons. Tomorrow, we are going